If you are starting organic chemistry reactions, there is one mechanism you absolutely need to understand first: acid-base reactions. The good news is that acid-base reactions are actually one of the simplest mechanisms in all of organic chemistry. At its core, an acid-base reaction is just a proton transfer. That is it. One molecule donates a proton, and another molecule takes the proton. Once you understand the electron movement, almost every acid-base reaction starts looking the same. In organic chemistry, acids and bases are usually explained using Bronsted-Lowry definitions. An acid donates a proton, a base accepts a proton, and the proton we are talking about is simply H+. Now let's discuss the mechanism itself. Every acid-base mechanism has two arrows. The first arrow starts from a lone pair on the base and points toward the proton on the acid. The second arrow starts from the bond connected to that proton and moves back onto the acid atom as a lone pair. And then on the product side, we will have a conjugate acid and conjugate base. The conjugates are always pairs to the original acid and base, and will always have an H+ difference, and be opposites of its pair on the other side. An acid will have a conjugate base, and a base will have a conjugate acid. This is extremely important. Electrons always move from electron-rich areas to electron-poor areas. That means arrows start from electrons, not atoms. The base is electron-rich because it has a lone pair. The proton is electron-poor because hydrogen only has 2 electrons in the bond. So the base attacks the proton, then the bond breaks and the electrons return to the acid atom. That is the entire mechanism. If you understand those two arrows, you understand the foundation of acid-base chemistry in organic chemistry. Now let's go through several examples. Example 1. Hydrochloric acid reacting with water. In this reaction, water acts as the base because oxygen has lone pairs that can donate electrons. Hydrochloric acid acts as the acid because HCl is a very strong acid and easily donates a proton. The chlorine atom is electronegative, which weakens the hydrogen-chlorine bond and makes the proton easier to remove. The oxygen lone pair attacks the hydrogen on hydrochloric acid. Then the hydrogen-chlorine bond breaks and the electrons move on to chlorine. The products are hydronium and chloride. Hydronium is the conjugate acid and chloride is the conjugate base. Example 2. Ammonia reacting with water. Ammonia acts as the base because nitrogen has a lone pair, and ammonia is a weaker acid with a relatively high pKa value. A higher pKa means the molecule is less willing to donate a proton and more likely to behave as a base instead. Water acts as the acid in this reaction. The nitrogen lone pair attacks a proton on water. Then the oxygen-hydrogen bond breaks and the electrons move back onto oxygen. The products are ammonium and hydroxide. Ammonium is the conjugate acid and hydroxide is the conjugate base. Example 3. Methoxide reacting with water. Methoxide is the base because it has a negatively charged oxygen. Negative charges make molecules very electron-rich, highly reactive and basic. That negative charge strongly increases the tendency to attack a proton. Water acts as the acid. Water is amphiteric, so it can act as an acid or base depending on the nature of the other reactant. The negatively charged oxygen attacks the proton on water. Then the oxygen-hydrogen bond breaks back onto oxygen. The products are methanol and hydroxide. Methanol is the conjugate acid and hydroxide is the conjugate base. Example 4. Hydroxide reacting with acetic acid. Hydroxide acts as the base because it carries a negative charge and has lone pairs on oxygen. Acetic acid acts as the acid because the acetate product formed afterward is resonance stabilized. That stabilization makes acetic acid much more willing to donate a proton. The hydroxide oxygen attacks the acidic proton on acetic acid. Then the oxygen-hydrogen bond in acetic acid breaks back onto oxygen. The products are water and acetate. Acetate is the conjugate base and water is the conjugate acid. Example 5, sodium amide reacting with ammonia. Sodium amide contains the amide ion, NH2 negative, which is an extremely strong base because of its negative charge. Negatively charged species are generally much more reactive than neutral molecules. Ammonia acts as the acid in this reaction because it can donate a proton. The negatively charged nitrogen attacks a proton on ammonia. Then the nitrogen-hydrogen bond in ammonia breaks back onto nitrogen. The products are ammonia and amide. This reaction is reversible because the molecules are closely related in acid-base strength. Now let's discuss one of the most important skills in organic chemistry. How do we identify the acid and the base quickly? A fast strategy is this. Look for lone pairs or negative charges to identify the base. Negative charges almost always increase basicity because they make the molecule electron rich. Look for acidic hydrogens to identify the acid. Hydrogens attached to oxygen or positively charged atoms are commonly acidic. And remember this important trend. Lower pKa means stronger acid. Higher pKa means weaker acid and usually a stronger conjugate base. Molecules with positive charges often behave as acids. Molecules with negative charges often behave as bases. Now let's go over some common mistakes students make. Mistake number 1, drawing arrows in the wrong direction. Remember, arrows always start from electrons. Lone pairs and bonds have electrons we can draw arrows from. Never start an arrow from the proton. The arrow should begin at the lone pair on the base and move toward the hydrogen. Mistake number 2, forgetting the second arrow. Students often show the base attacking the proton but forget to break the bond on the acid. If hydrogen already has one bond, another bond cannot form unless the original bond breaks. Hydrogen has a duet of 2 electrons. Other elements have octets. Exceptions are boron, and C+ atoms lack octets and have 6 electrons. Mistake number 3, ignoring formal charges. After the reaction, always check charges carefully. Formal charge equals valence electrons minus bonds minus dots. Mistake number 4, choosing the wrong proton. Not every hydrogen in a molecule is acidic. Hydrogens attached to oxygen or positively charged atoms are usually much more acidic than hydrogens attached to carbon. Mistake number 5, memorizing reactions instead of understanding electron flow. In organic chemistry, reactions become much easier when you focus on where electrons move instead of trying to memorize every reaction separately. And that is why acid-base chemistry is the perfect first mechanism to learn. Because once you understand proton transfer and electron flow, you are already building the foundation for substitution reactions, elimination reactions, alcohol chemistry, enolate chemistry, and many more reactions later in organic chemistry. So if you remember one thing from this video, remember this. An acid-base reaction is simply a proton transfer driven by electron movement. The base uses a lone pair to attack the proton. The bond breaks and becomes a lone pair on the acid. That pattern repeats throughout all of organic chemistry.